So good morning all of you. This is the second lecture on path loss and shadowing. Before we go ahead with the today's portions, we'll have a quick recap of what we have done in the previous session. In the previous session, what we have done is that we have learned about the basic definition of what is a path loss, what is free space path loss. We have learned what is shadowing, reflection, refraction, diffraction, etc. Okay, in this class we will be learning fading, multiple types of fading that is happening within the electromagnetic waves that is being transmitted from one point to the other. So fading in wireless channels. The received power, as we have already discussed in the previous session, received power at one particular point of time is inversely proportional to the square of the distance between the transmitter and the receiver. The received power at a distance d, PR, is expressed by a very famous equation called as Friis free space equation. The power received PR at a distance d is given by PR of d is equal to power transmitted, that is PT, GTGR, transmitter and the receiver gain antenna respectively. Lambda is the wavelength, d is the distance, L is a system loss factor. PL, in the last slide, in the previous slide, we have seen a graphical representation of the received power at a particular distance in dB. We have three components: free space path loss, shadowing, multipath loss. When we consider all these things, we'll get the linear path loss in dB. Linear path loss in dB is given by 10 log to the base 10 PT by PR in terms of dB. The received power at a particular distance d is given by the famous Friis free space equation. The gain of the antenna is given by its effective aperture. Okay, effective aperture AE. G is equal to 4 pi AE by lambda square. According to the Friis free space equation, we have to calculate the gain of the transmitter and the receiver antenna to find out the power received at a particular distance. Am I right? So now, how to calculate the gain? Gain is given by 4 pi AE by lambda. The effective aperture AE is related to the physical size of the antenna, and A is related to its carrier frequency, that is lambda wavelength, you know, as such is the inverse of frequency. Lambda is equal to C by F, and when we substitute, we get the wavelength dependence. So the gain of the antenna, transmitter antenna and the receiver antenna, depends upon two factors. One is called as the effective aperture, which depends upon the area of the antenna. We have a transmitter antenna GT, gain of the transmitter antenna represented by GT, gain of the receiver antenna represented by GR. The gain is equal to 4 pi AE, effective aperture by lambda. Now we'll see an important definition which is called as effective isotropic radiated power, EIRP. The received power falls off as the square of the distance between the transmitter and the receiver. This implies that the receiver power decays with distance at a rate of approximately 20 decibel per decade. An isotropic radiator is an ideal antenna which radiates power with a unit gain uniformly in all directions and is often used as a reference antenna in wireless systems. An isotropic antenna is an ideal antenna. We are presuming an ideal antenna with which transmits power in all directions almost equally. An ideal scenario that never exists. But we'll be using it for all our theoretical and academic purpose. And this definition might come to your question paper directly. Define effective isotropic radiated power, EIRP. EIRP is the product of the power transmitted and the gain of the transmitted antenna. The antenna is assumed to be an isotropic ideal antenna. Define effective isotropic radiated antenna. There could be a 3-mark question for this. And this is the definition. Definition is given to you very clearly. Product of the transmitted power and the gain of the transmitter antenna. Now the linear path loss PL in dB, we are substituting the equations from the previous equation. Okay, PT by PR, what we'll get is that the linear path loss PL in terms of dB is 10 log to the base 10 PT by PR. That is equal to 10 log to the base GT GR lambda square by 4 pi whole square D square. On substitution, we'll get like this. And now we have already calculated that, we have already derived the equation for PT. Substituting that, we'll get the linear path loss PLDB is equal to 10 log lambda square by 4 pi the whole square D square. When the antenna gains we are excluding, the antennas are assumed to have unity gain. That is, we are assuming that GT and GR is equal to 1. In that case, we'll get the linear path loss PL in terms of dB to be equal to 10 log lambda square by 4 pi square D square. This is the answer to the question. Derive the linear path loss in a wireless communication system, PL in terms of dB. Is that clear? Can we go to the next? So here in this slide we will be seeing what is meant by Fraunhofer region or what is far off region. The free space model is valid only for the received power values of which D is far field of the transmitting antenna. In reality, while you implement a practical wireless communication system, there might be situations where you do not know the distance between the transmitter and the receiver. So there might be far off regions where D may be infinity. These regions, the far off regions, are called as Fraunhofer regions. The far field or the Fraunhofer region of the transmitting antenna is defined as a region beyond the far field distance D, which is related to the largest linear dimension of the transmitter antenna aperture and the carrier wavelength. The Fraunhofer distance df is equal to 2d square by lambda, where d is the largest physical linear dimension of the antenna. So to be in the far field region, df should be much greater than d. Previously in the last session, we have seen what is large scale fading. Today we'll be seeing what is a large scale propagation model, and we'll see what happens when we are going to design a model which is a large scale, which covers a larger area. The large scale propagation models use close in distance d naught as a known received power reference point. We take a reference point d naught for designing our propagation model. The received power PR at a distance d, which is much greater than, not much, which is greater than d naught, may be related to PR d naught. This is a practical way in which we design or we find out the coverage area of a base station. The value PR d naught may be predicted from Friis free space equation. Friis free space equation, we can predict short distance power. What is Friis free space equation? PL is equal to P received, PR is equal to PT GT GR lambda square divided by 4 pi whole square d square. With this d is the distance, we will find out the Friis free space equation for the power received at a particular point using d naught as a distance. D naught is a reference point which we are creating for generating a large scale propagation model. The value of power received PR at the distance d naught may be predicted by Friis free space equation. The received power in the free space at a distance greater than d naught is given by PR at d is equal to PR at d naught into d naught by d the whole square, where d is in between d naught and df. df is the Fraunhofer or the far field region. Okay, understood all of you? Now the received power in dm will be the linear power PL. dm will be 10 log to the base 10 PR d naught by 0.001 watts plus 20 log d naught by d. Did you understand the use of Friis free space equation? Do you know how to design or how to understand the power, how to get the value of the power received at a distance when the power at the reference point is given to you? Considering a reference point d naught, how we will find out the power received at the distance d? Next is a very important model called as two-ray model. We are expected to design, we are expected to simulate two-ray model. We have a Python program to simulate a two-ray model. I will show you the program and explain to you how it is going to work. But before we go to the program, we'll understand what is two-ray model, what is multipath propagation. As we have discussed earlier, when an electromagnetic wave is transmitted from a transmission point, this wave is expected to travel through different paths. Some would be a line of sight path, some would be non-line of sight path, some would be reflected, refracted, diffracted, and so on. So the same signal is received at the receiver point with multiple paths. So here we will presume a two-ray model, and then we will design a channel model for multipath propagation. So multipath propagation is caused when the transmitted signal travels through multiple paths such as straight line, or may be reflected at a large building or scattered at smaller obstacles. The two-ray model is used when a single ground reflection dominates the multi-path effect. The received signal consists of two components: the line of sight component or the ray, which is just the transmitted signal propagating through the free space, and a reflected component or a ray which is transmitted, which is the transmitted signal reflected at the ground. In two-ray model, what we are seeing is that, suppose this is the transmitter and you have a receiver here Rx. There would be a direct one way, one ray. Another one would be, suppose this is the ground, it would hit and reflect. So let us consider two paths. This is called as two-ray model. Considering these two paths from transmitter to receiver, let us consider one straight line path, another one reflected from the ground back to the receiver. Due to the finite speed of light, signals traveling along the different paths with different lengths arrive at the receiver at different time. The effect that is caused is called as delay spread. The original signal is spread due to different delays of parts of the transmitted signal. So what is meant by delay spread? There are two or different multiple paths that is being taken by the transmitted signal to reach the receiver. When you travel at different routes, you take different times to reach the destination, right? The same thing happens with the signal also. It travels through different paths and it takes different time to reach the destination. The change or the time taken for the signal from the first received signal to the next set, the last received signal, this time gap is called as delay spread. And these things will be very commonly used in your future modeling. So you should understand the definition of delay spread very clearly. What is meant by delay spread? This effect caused by multipath propagation is called as delay spread. The word delay spread is not visible because of the can. The word here is delay spread. The original signal is spread due to the different delays of the parts of the signal. Now you can see in this diagram, this is the transmitted signal, or this is a transmitted antenna, and here you have this user in the car. He's traveling. This gets, you have a direct line of sight. The same signal gets reflected from a building and it gets scattered from other. So when a signal is transmitted, it travels multiple paths. So here we are going to study, or we are going to design a mathematical model for multipath propagation. So here we can see that the signal received at the receiver will have different points. The line of sight will have higher power. The received power will be higher from the line of sight. You have other multipath, different ways where you have different range of powers for the transmitted signal. Is that clear for all of you? So this is a diagrammatical representation. Again, you have the transmitter, you have the transmitter here. Transmitter is always at a higher point than the receiver. So you have line of sight, you have this model is called as two-ray model. We are going to derive the equations for two-ray model in the coming slides. The received power PR, as we have seen already, PR will be equal to PT GT/GR into HT/HR by D square, the whole square. Okay, HT and HR is the height of the transmitting and the receiving antennas respectively. So now this graph is what we are going to study. It is interesting to note that two-ray model is independent of the frequency. The power received at the receiver is not depending upon the frequency. Understood, all of you? This could be a question, or this could be an important significance of two-ray modeling. We have the power received at the receiver, which is depending only on the transmitted power, the gain of the antennas, height of the transmitting and the receiving antennas, and distance between them. The power PR in DM will be equal to the power transmitted PT in DM plus 10 log to the base 10, the gain of the transmitter antenna, or plus 20 log to the base 10 HT into HR minus 40 log to the base D log to the base 10 of the distance between the transmitter and the receiver. You might be asked the problems on finding out the power received at different points using different equations, whatever we have studied today. Shadowing. After we have studied two-ray modeling, now we'll see the effects of shadowing in a signal. A signal transmitted through a wireless channel will typically experience random variation due to blockage from objects in the signal path, giving rise to random variations of received power at a given distance. Such variations are also caused by changes in reflecting surfaces and scattering objects. So a channel model has to incorporate all such variants needed to be studied. The location, size, and dielectric properties of blocking objects, as well as the changes in reflecting surfaces and scattering objects that cause the random attenuation, are generally unknown. So statistical models must be used to characterize this kind of attenuation. The most common model for additional attenuation is known as log normal shadowing. So what we'll be studying is what is log normal shadowing. Okay, last time or previously somewhere I have read that a question in multiple choice have come. What is the best method for modeling a statistical modeling of attenuation in wireless channels? For shadowing, we use what is called as log normal shadowing. So good